Okay, so the third example that we started in the lecture was one that we just got started, and I left you to have a look at it in your own time. So I'm going to do the same getting started here. So what we started with was a definition, which I'm going to abbreviate defin. And that is that n choose k is the number of ways of choosing k objects from a collection of n objects. So let's see if we can get a handle on this definition. Whenever you see a definition, the first thing you should do is try and think up an example that meets that definition. Then after you've played with examples for a bit, sometimes it's useful to also think up counterexamples. But certainly start with an example. So I asked the students in the lecture to come up with an example of a small set of favourite items, and they came up with a set consisting of bird, cat and dog, which I'm just going to write as B, C and D. And my question for you is, if k is equal to, so n equals 3 here, if k is equal to 2, then give me an example of a set of 2 things that's drawn from this set of 3 things. And the student said, well, bird and cat. Yep. Is there another way that you could choose 2 things from this collection of 3 things? And they said, well, yes, you could have bird and dog. And is there yet another way? Well, yes, you could have cat and dog. And a student pointed out you could also have dog and cat and so on, flip them all around. But that would be the same set. So it turns out we've got 3 ways to choose 2 things from a set of 3. What if you just wanted to choose one thing? How many ways would there be to do that? And the answer was, well, exactly 3. What if we wanted to choose no things at all? Well, that's a sort of trivial, vacuous thing to do, and there's just one way. And what if you wanted to choose all 3 of them? Well, there's just one way to do that as well. So if we had time, we would play around for a while with bigger sets. Try 3 things, try 4 things, try 5 things, try a smaller set, try 2 things, 1 thing, even 0 things. And after we got a chance to play around for a while, we might notice a pattern. N choose k is equal to n factorial, n minus k factorial, k factorial. So at that point, this is our conjecture, or indeed our claim. Conjecture. The thing that we believe is true and want to prove. So now what we're going to do, and we believe it's true for all n and for all k such that 0 is less than or equal to k, less than or equal to n, because those are the values for which it makes sense. Now, we want to prove it by mathematical induction. And as was pointed out by one of the students, for a base case, we could take n equals 0. Often though, taking n equals 1 is more informative, helps your intuition more, even if n equals 0 is going to work. So I'm going to look at the n equals 1 base case. So that says that 1 choose k is equal to 1 factorial, 1 minus k factorial, k factorial, for 0 less than or equal to k less than or equal to 1. Let's write that out more explicitly, because if we look over here, we can see there's really only 2 values of k. That's the claim that 1 choose 0 is equal to 1 factorial, 1 factorial, 0 factorial. And it's also the claim that 1 choose 1 is equal to 1 factorial on 0 factorial, 1 factorial. Now, 0 factorial is equal to 1 by definition. And 1 factorial is also equal to 1. So this says that this is 1 divided by 1 times 1, which is 1. And it also says that this is 1 divided by 1 times 1, which is 1. So if you've got a set of just one thing, let's say just a bird, and you want to choose 0 things from it, how many ways to do it? Exactly 1. And if you want to choose one thing from it, how many ways? Exactly one. So that means that we're happy that the base case holds. So this is a continuation of example 3. Recall that we gotten to the point where we had a conjecture that we were trying to prove or claim that n choose k is equal to n factorial over n minus k factorial for all natural numbers and for all k that is also a natural number such that 0 is less than or equal to k is less than or equal to n. That was a such that there. Such that. Okay. We had already done the base case. So now we're looking at the inductive step, and I'm just going to give you some initial hints. All right. Remember that when you're trying to prove a for all statement, the inductive step requires an inductive hypothesis. Inductive hypothesis, where you assume that the claim holds for one particular natural number. So we're assuming that there exists, now we can't use k because we've already got k, so let's say m. There exists m in the set of natural numbers such that for all k in natural numbers between 0 and m choose k is equal to m factorial over m minus k factorial k factorial. And what you now want to do is you want to consider what happens for m plus 1, because we want to be able to get from the mth to the m plus 1 stepping stone. So we say m plus 1 choose k is equal to what? Well, you're going to need a separate little result. You're going to need a lemma or something to convince yourself that that can be written in terms of m choose k and m choose k minus 1. Separate proof. So go off and do that separate proof, check it, check I've got it right and do it, and then follow your nose and see if you can complete the inductive proof. That is, if you can complete the inductive step.